All right, sorry I'm 10 minutes late. I apologize. But let's get going. So we're talking about chemistry for this is our last chemistry unit. What you guys? You're not chemistry fans? Astronomy's coming. I'm in the middle of putting together the first Earth science one, and it's all about rocks. And I'm like, okay, I'm not a huge fan of rocks, but we'll get through it. So, not to give you foreshadowing it's going to be boring or anything, but it's about rocks. The Earth's crust is pretty cool, for what it's worth. But anyway, so today we're going to talk about chemical reactions, two different types of chemical reactions, namely acid-base reactions and what's called oxidation-reduction reactions, which are both they both involve transferring of elementary particles. And we'll get into that. And then we're going to talk about organic compounds. And organic chemistry is another one of these fields that's gigantic. And in fact, when we get into talking about organic chemistry, I'll explain a little bit more about that. But those are the two big things we're going to talk about tonight. And then, as I said, we will be done with chemistry. OK, so let's start out with this class of chemical reactions called acid-base reactions. Okay, you have all heard of acids and bases, I hope. Anybody give me an example of a typical acid that you see every day in the chow hall?
Citric acid.
Citric acid in what kind of?
Lemon wedges.
Lemon wedges, orange juice, limes, that sort of thing. Have any of you guys, have you ever taken those? I guess they have lime wedges. And if you squeeze out some lime juice and you happen to squeeze it out into one of those styrofoam containers, like this styrofoam container or one of the cups or something like that, you know what it does? It dissolves it instantly. Okay, it's actually an acid-base reaction going on right there. It's kind of gross. You're like, look, why is my styrofoam dissolving? Am I consuming that? And the answer is probably you are. But anyway, that's a typical type thing. The other one might have been vinegar. Vinegar is another acid, right? Okay, and when you think about acids, they're generally sour, right? Lime juice, orange juice isn't too bad, but it's got a lot of sugar in it, orange juice. Lemon's kind of sour, lime's somewhat sour. But acids are extremely important to the chemical industry, actually. There's sulfuric acid, which is a strong acid, and in fact, the #1 manufactured chemical in the entire world. Tom, you said you do some things with chemical. Tom, you use it all the time in what field?
Solar panel industry.
In the solar panel industry, yeah, you'd absolutely use those kind of chemicals there. And in fact, sulfuric acid is so heavily used in industry that the amount of sulfuric acid that you produce as a country is actually an indicator of your country's industrial strength. Like they look at it and they say, oh, look, Somalia has very little sulfuric acid production. Well, because they have very little industry. So et cetera, et cetera. The United States, we produce huge amounts of it because we use it all the time. So very important in terms of the acid. Now, bases, on the other hand, generally, I guess you could think of them as kind of bitter tasting if you're going to taste them. And they feel a little slippery, right? So if you've ever had bleach on your hands, or for that matter, soap, which is generally basic, it slips a little bit. Now, it's not actually the base itself that's doing the slipping. It's the oils in your hand are actually coming off of your hand, and that's what's doing the slipping. So, kind of cool. Okay. The term alkaline comes from the Arabic word for ashes, which is what happens, when you burn something, right? You end up with ashes. If you get water, if you take those ashes and put them in water, it's very slippery, and it's because ashes tend to be basic when they're in solution like that. Okay, and it's actually this base potassium carbonate, K2CO3. Okay, so we're talking, yeah.
Is an alkaline like a battery?
There are alkaline batteries. In fact, we're going to get into batteries a little bit later this evening. But yeah, alkaline batteries are batteries made with alkali metals. Okay, all right. So here's the difference when we talk about acids versus bases. Okay, acids are chemicals that donate a hydrogen ion, H+. Okay? So what that means, and we'll see the actual formula here, or we'll see this in action in some formulas. But just for now, just know that, look, if you're an acid, you're going to take a hydrogen ion, okay, and you're going to donate it to some other some other chemical that's in the solution that you're in. Okay, a base is the exact opposite. Okay, it's a chemical that accepts a hydrogen ion. Okay, and we have this acronym BAD, B-A-A-D. Okay, I'll write it over here. B-A-A-D, which is B-A-A-D. Bases accept a hydrogen. Acids donate a hydrogen. Okay, so that's how you can remember it. Okay, if you remember this B-A-A-D, you can say, all right, which one's which? Oh yeah, the bases are the ones that accept a hydrogen ion, and the acids are the ones that donate it. Okay, B-A-A-D. And by the way, a hydrogen ion, right? Remember what a hydrogen looks like? It's number 1 on the periodic table, which means it has how many protons? 1 proton, right? Sitting right there in the middle of the thing. And a hydrogen actually has a little electron out here flying around in its little electron cloud, right? If it's an ion, it means it's actually lost that electron. So what's a hydrogen ion? But what is it? What's in the middle of, what's in the nucleus? What is it? What 2 particles are in the nucleus of any atom? Protons and neutrons. What is this? What's in this nucleus? Protons, no neutrons, right? And there's only 1 proton. A hydrogen ion is simply a proton. That's all it is. Okay, so it's talking about donating a proton or accepting a proton in this chemical equation. And we'll see what that means in probably one more slide. Okay, but that's all it is. So when we talk about bases and acids, start thinking, hydrogens, okay? All right. Aha, here we go. So let's look at a combination of hydrochloric acid, which is H and a Cl, hydrogen and chlorine, when you mix it in water. Okay? Well, this is what a HCl atom looks like. It's got 1 chlorine there, and it's got a little hydrogen, which is just a proton, remember, sticking off the side. Okay? When it's in water, well, it turns out that the water grabs on that hydrogen and makes a little molecule like this, okay, which has 3 hydrogens, 3 protons, and the chlorine has no extra protons anymore. So what did the chlorine do to its hydrogen? It donated it to the water. Okay, so if it's donating, acids donate. So in this case, hydrochloric acid, which you can tell by the name, HCl is an acid. Okay, so it does take another. Let's look at this other example. If you have water and NH3, okay, which is, anybody know what that is? NH3. It's not an acid at all, actually. No, you're close. It's not nitrogen. It's ammonia. Okay, that's what that is. When you take H2O, water, and what's that?
They use it for films.
They use it for like pictures and things, probably. Yeah, when you're developing film, and by the way, I don't even know if you guys nobody even develops film anymore, really. Some people do, but not often. They use lots of chemicals because there's got to be lots of chemical reactions going on there to make the film to develop it. But anyway, when you get water and an ammonia, when you get ammonia to mix together, well, look what happens. The hydrogen donates a proton to the ammonia. Okay, so the ammonia does what? It accepts a proton. Therefore, it is a base. Okay, ammonia is a base. Well, and you can see it here. It's got now, instead of 3, it's got 4 protons. Okay, and by the way, once the water gets rid of that proton, okay, it now has a slight negative charge because it's lost that positive proton. And the ammonia has a positive charge because it's gained that proton. Okay, so we get the idea here. It's all about donating or accepting protons. Now I have a question for you. Is water an acid or a base? Or I guess neither.
Water?
Water, yeah.
If there's anything in space,
It's accepted.
Ah.
he's an acid.
Since we got 1 acid, 1 base, we've got 1, not sure, we've got 1 that says it's both. Let's go back and look here. Up here, what did the water molecule do? It accepted a hydrogen, which means it's what? AD. It is the, sorry, Ba, bases accept. So in this case, it's what? A base. Right? When it mixes with an acid, water happens to be a base, or at least it acts like a base. Okay? And down here, if you look down here, the water is giving up, is donating the proton. Therefore, in this case, the water is actually the acid. Okay, so yeah, so it's both. Okay, and I think the next thing is the same exact slide. Yeah, so it's sometimes acts as a base, sometimes acts as an acid. So it's both. Water is, in this case, one of the kind of a neat thing about water is that it can do both, and that's why you see so many solutions with water in them, because water has this neat property that A, it's a liquid at room temperature, B, it does all this I'm a base, I'm an acid, whatever you're mixing into it, it kind of acts as the other thing to that substance just because of the way it's constructed. Okay? All right, so that's acids and bases in general. An ammonium ion can act as an acid. Okay, so remember, this one's just ammonia. NH3 is ammonia, the molecule, the chemical. It's just ammonia. Once it becomes positive, it's actually, we call it ammonium. Okay, and I'm not going to worry about all the details. You do have to kind of recognize some of these terms. But it becomes ammonium when it's in solution. And guess what? That ammonium is not just going to sit there and hold on to that proton forever. In certain circumstances, when it bumps the right way against an OH minus, okay, called a hydroxide, which we'll get to, it can actually give that proton back. So in this equation, and notice the arrows going the other way, the ammonium is actually the acid because it's donating the proton. Okay? And what's happening is this reaction is happening kind of all the time in solution. Some of the ammonias are turning into ammonium. Some of the ammoniums are turning into ammonia, back and forth. It's not a 100% stable solution. Okay? It is in what we call equilibrium, which means that the same number, eventually, the same number of ammonias are turning into ammoniums, and ammoniums are turning into ammonias at roughly the same rate. So you've got this equilibrium condition, but it's still happening back and forth. Okay? And remember, there's billions and billions and billions and trillions of these molecules in like just one cup of solution. So it's not a wonder that this thing's happening kind of continuously. There's lots of bouncing going on and lots of transferring back and forth of these particles. Okay? And by the way, when we write this in a forward and reverse reaction, we write it with a double arrow, one going one way, one going the other way. Okay? What's that?
It's reflexive.
It's
Both ways.
when you say, what do you mean? Oh, it's reflexive. Yeah, it goes both ways in the sense of going. The reaction's happening in both directions at the same time. Okay. All right. Okay. So let's talk for a minute about ionic acid-base reactions. Now, we're not talking about anything different here, but when you look at a reaction between an acid and a base, okay, you end up with this thing that we actually technically call a salt, okay, and I don't just mean sodium chloride, okay. When we talk about salt, the stuff you put on your French fries, that is a salt. It does fit into this definition, but it's not the only salt. Okay, salt is a chemical term that means any ionic compound. And remember, ionic compound was when you got a complete transfer of those electrons formed from the reaction of an acid and a reaction from an acid and a base. Okay, so you take an acid, you take a base, you mix them together, and you guys have probably done this, where you take vinegar and you pour it onto some like baking soda, and it bubbles all up and whatever, right? Well, the baking soda is a base, and the vinegar is an acid, and you've got this reaction forming, and it actually forms a salt, okay, at the end. All right, so that's what a salt is. Now, let's take an example here. If we look at hydrochloric acid, same thing as we had before, and potassium hydroxide, which is KOH. Okay, let's look at this little reaction here. You've got HCl, hydrogen chloride, and KOH. Well, the hydrogens and the oxygen hydrogen part get together, right? And they form water. And the other two, the K and the Cl, produce this potassium chloride, which is just that salt. Okay, so you get that salt from this reaction, and you get the salt in the water, and you just get salt water. Again, it's not salt water like French fry salt. It's KCl. And by the way, you can buy, I don't even know what they call it, low salt or no salt or something like that. And it's just KCl, which has less sodium in it, and they say sodium is responsible for high blood pressure and so forth. So you can buy that. Of course, the problem is potassium chloride has its own side effects and problems, like, I don't know, epilepsy or something like that. I'm not sure what it is. It actually says in the book. I forget. It says in the book what the actual other side effects are. So yeah, right under that picture right there that you're looking at. Really. What does it say?
Serious illness.
Serious illness? Yeah. Well, it's not so great. You probably, if you're going to buy any kind of like low sodium salt, it should probably be that, like, it shouldn't be no sodium salt probably. But I'm not a doctor, so take that with a grain of salt. Well, that was a good joke. I even just thought about that. All right. Anyway, salts are actually less corrosive than the acids and bases which they form. Part of the reason is, if you look on your periodic table, which many of you hopefully still have somewhere, if you look on your periodic table, remember, like in this case, potassium is all the way on the left, okay? And chlorine is almost all the way on the right, next to the noble gases. Those two react so well together that they don't want to bother trying to react with anything else. So when you have KCl, it's like perfectly fine, right as it is, to not worry about reacting with anything else, so it's not going to corrode stuff. Okay? Chlorine on its own, chlorine gas, highly corrosive. Potassium will blow up like we saw in that video last week if you put it in water, so very reactive. But together, once they're a salt, not so corrosive. Okay? When you mix acids and bases together, you end up with this neutralization. Okay, that's what we call it. We call it neutralization, and it just means you've neutralized the acid and the base. Okay? So that's where we're at. Okay. All right. When you talk about acids and bases, you can talk about how strong they are. Okay? And the strength has to be, or has to do with how readily they do that donation or accepting process. Okay? A couple examples, hydrogen chloride and sodium hydroxide, both very strong. Hydrogen chloride being a very strong acid, sodium hydroxide being a very strong base. Okay? They both happen to be very corrosive. Okay? And meaning that you don't want to like pour HCl on yourself. Okay? Although you guys each have many ounces of HCl right now in a somewhat accessible location. And Tom's what's that?
It's your stomach.
It's your stomach. Yeah, your stomach, the way you start to digest food is in your stomach, and it's got lots of hydrogen chloride in there, okay? Which is why it's kind of gross and doesn't feel so good when you throw up, like, you know, in your throat and all that, right? Because it's just gross, because it's hydrochloric acid, which is very corrosive. Why doesn't it corrode away your stomach? Well, your stomach's coated in mucus, and which isn't reactive, and so on and so forth, right? So you can end up with issues. People who have ulcers, they're so painful because there's actually like a little hole in your stomach where the hydrochloric acid can like eat away at the stomach lining. Not so good.
It's like acid reflux.
Acid reflux is hydrochloric acid ending up in your esophagus and your throat and so forth, and that's bad news. Okay, I mean you should get it taken care of because that's bad. Okay, what's that? Nexium. Is that a chemical that you use to get rid of it? Is that a medicine? Oh, all right. Well, there you go. There you go. So that's the difference. Now, you can actually it doesn't. Well, let's just say for now, strong acids and bases, okay, they generate many of these ions when they're added to water. Okay, weak acids and bases, not so many ions, meaning they don't do so well at the whole donating or accepting of hydrogen part. They do all right, but not so great. Examples of weak acids, the things you see every day that they don't really bother you, like citric acid, relatively weak. Vinegar, relatively weak. Acetic acid, relatively weak. So the acids that are you generally deal with all the time, not so strong. But if you need to do something like clean out your drain because it's got hair stuck in it or something, you're going to use something that has HCl in it, right? Because it's a really strong acid. Yeah.
Now, when you combine sulfuric acid and water,
When you combine sulfuric acid and water, yep.
it gets really hot.
It does get hot.
What is the reason behind that?
Good question. So, good question. When you mix sulfuric acid and water, okay, what's happening is you're doing this ion exchange, but it happens to be what's called an exothermic reaction, which we mentioned last week. Okay, and that's why it gets hot, because you actually get energy out of the reaction itself, which manifests itself in a temperature increase. So yeah. And by the way, do you know so if you have water and you have acid, you want to mix them. Okay? Which order are you supposed to do it in? Pour the water into the acid or the acid into the water? Do you guys know?
Acid into water.
Pour the acid into the water, because generally you're going to dilute it more. And if you pour water into acid, if you drop a little bit of water into acid, the reaction can be strong enough so that it actually boils the water, which splatters it around. So that's bad news. So the other way around, you're less likely to do that.
Yeah, because we get percentages of sulfuric acid.
You get percentages of sulfuric acid?
Like a 30% solution.
I see. So you get like such and such molar solution concentration. Yeah. And you mix it down in the water to some other lesser concentration, right? Okay. All right. How do we actually test the strength of an acid or base? Well, you can figure out which one actually has more ions. Okay? And you can do a little test with a light bulb if you want. If you take a glass of pure water, okay, regular pure water, deionized, if you want to call it DI, is that what they call it? Yeah. And you put the two leads of a light bulb with a battery and everything in there, okay, you're not going to get any light. Because water, contrary to what people think, plain old pure water does not conduct electricity very well. Why? Well, there's no way for the electrons to flow through the water to make that current, because there's no ions, and the ions really are the ones that are charged. So there's no way for that electricity to flow through. Kind of a little bit morbid for a second, but when people get electrocuted for the electric chair, okay, I don't know if you ever noticed, they take a little sponge and then they put the little things in there. Well, that sponge is not just water; it's actually salt water. Okay, they have a little salt water solution, and they do that, and that's so they get a nice, good connection between the electrode and your hand, so that you get electrocuted, right? Yeah. So I mean, it's good. The first guy that was electrocuted, actually, it took them like 3 jolts to get him before they finally, knocked it out. But not good. I haven't seen the Green Mile.
You haven't seen it? It's a great movie.
Is it?
But there was a part where the guy that he's supposed to put the wet sponge on the guy's head.
Oh yeah.
He doesn't get it wet.
Oh, okay. The guy doesn't get it. That's pretty. I bet it is. Yeah. So anyway, so if you take a strong acid, this is still a little tough to see on the board here, but if you take a strong acid and you do the same little test, okay, you get a nice bright light going here, because you've got lots of ions in there, and you can make a strong current go through the solution, and it works great. Okay, and if you take a weak acid, you don't have as many, so this is actually a less lit up light bulb than that, so you can kind of tell. Okay, so that's one way to tell if you've got a strong acid or a weak acid. Okay, strong acids actually completely ionize in water, so all the acid actually ionizes. In weak acids, not so much. Okay. All right. Strong acid solutions aren't necessarily corrosive. It's not like, oh my gosh, I have a strong acid here in solution, and it's going to corrode everything it touches, right? It's actually, remember, it's about the number of ions that are actually in the solution. Okay, so you can actually dilute strong acids and be fine with it. Okay, you could take hydrochloric acid and you could dilute it down enough, and you're fine. I mean, it's not going to, burn anything, right? Because it's just dilute. One of the strongest bases, as I said before, sodium hydroxide, NaOH, one of the strongest bases, but you use it every night when you brush your teeth, right? That's what kind of cleans off your teeth. All right, and it's strong base, but they have a tiny little amount in there, so the solution is not that toxic in that case.
Same thing with fluoride in toothpaste.
Fluoride in toothpaste, same thing. Yeah, that's actually a basic solution. I think it's a basic solution of fluoride. forget which solution it is. But anyway, the fluoride in your toothpaste is a low enough concentration that it's not going to corrode away your teeth. You hope. But that's what you hope.
Chemical will, if you get it on your skin, it'll seep in your bones, beneath your bones.
Yeah, exactly. Exactly. OK, so here's a question for you. Can water be absolutely pure? Can you absolutely purify it? Well, of course, the answer is going to be no, right? But here's one of the reasons you can't. You could get everything out of the water that's not hydrogens and oxygens. OK, and you'd think, oh, OK, then I have pure water, right? Well, you really don't, because remember that water can be an acid or a base. Well, it turns out that it will react with itself a little bit. I mean, a very little bit, but a little bit. OK, water donates an electron to water. I'm sorry, donates a proton to water. OK, and you end up with hydroxide, which is OH minus, and hydroniums, which are H3O plus. OK, 3 hydrogens and an oxygen. And you've had water actually acting as, well, it's donating here, so it's an acid, and it's gaining here, so it's a base. And so therefore, it acts as both an acid and a base in solution. You're not going to get much, but you're going to get some. Yeah, Louis.
What is H3O? Like hydrogen?
Let's look at what H3O is. Right? It's got an oxygen and 3 protons on it. Right? Oxygen and 3 protons. Therefore, it's got an extra proton, and if it had the same amount of electrons as before, it's going to be 1 more proton, so 1 more plus. So it's an ion, a positive ion of that molecule. Okay? And it's only in solution. Like, you're not going to see hydroniums floating around. They're just not going to do it. Or in your, sure, they're in your water because they're in solution, but they're not, it's not a chemical that's going to be out and about by itself. Question?
Yeah,
Andy?
I've heard the term acid rain, but I've never heard like
Good question. We'll get to acid rain in a few minutes. Okay? And you guys read about it this week for this chapter. But we'll talk about it in a minute, about why we have acid rain and not basic rain. Good question. OK, so anyway, let's get these two terms out of the way. We've got hydroxides, which are OH minuses. In fact, I'll write this down over here. OK, we've got hydroxides. Hydroxide, OH minus. OK, and hydroniums, which are H3O plus. OK, an extra little proton on there for that hydronium. OK, it's going to be important in a minute. OK. If you look at a solution with water, anything that's got an acid in it or a base in it or whatever, if you look at the concentration of these hydroniums and the concentration of these hydroxides, it turns out that something very cool is happening. You end up with, if you add them together, you end up, well, if you look at the concentrations of them, the total concentration of hydronium and hydroxide is constant. And it's a very, very, very small number, 1 times 10 to the negative 14th of them. Okay? Part of the reason they're there at all is because the water reacts with itself in pure water. But if you've got an acid, okay, if you've got an acid, you've got lots and lots of hydroniums, okay, and not many hydroxides. And if you're in a base, you've got lots and lots of hydroxides and not many hydroniums. And that's because of this idea that in an acidic solution, you've got lots of donating of these protons. So what is it donating them to? The water. And the water ends up very positive. Like, it ends up as hydroniums, which is a positive. And so you've got more of that. But it's always this balance beam. Okay? It's always if you get rid of some hydroniums, you're going to end up with more hydroxides because of the solution. If you add them together, you end up with 1 times 10 to the negative 14th total concentration of them. Okay? Which is kind of interesting, okay, because we use that when we talk about the next thing, which is, I think, pH. OK. I hope you've all heard of the pH scale in some form or another, right? Eric, have you heard of the pH scale? OK. So pH, we actually have a definition for pH. Now, what pH is, bottom line, no kidding, pH is the measure of how much a solution is either a base or an acid. okay, or neutral. But it's either a basic or an acid, and how much it is that measure of pH. But we're going to talk a little bit about the math behind how this is the case. Okay? What pH is defined as is, seems like a strange definition, but we'll see why it makes sense in a second. pH is defined as the negative log, I'll get to what that means in a sec, of the hydronium ion concentration. Okay. What that means is if you know the concentration of hydroniums, okay, you do this weird function called log on it. You take the negative of it. That's your measure of pH. Okay? Well, the brackets just mean the concentration. Okay? And the log part, we'll talk about that, what that means in a little bit. Okay? It is not hard. This is like the most basic like trigonometry sort of, well, it's not even trig, but I guess you learn about logs probably the first time in trig or pre-calculus or something like that, but it's not hard. Okay? And you probably did it in high school at the very least. Okay, but what is a log? Anybody remember what the definition of a log is? If I said to you 10 cubed, and I wanted to take the log of that, the log of 10 cubed, it's just the power that 10 is raised to. That's all a log is. Okay? Pretty easy. Okay, exponents and logs are inverses of each other. Okay, so you got 10 to the 3. So if I said, what's the log of 10 to the 3, you'd tell me, no, just the log, just 3. Okay, so if we talk about 10 to the 3. Now, let's see what this looks like in terms of other. I bet you can do all these other ones too. Okay, 1,000 has how many 3's after it? 3. So what's the log of 1,000? 3. 100, what's the log of that? 2. What's the log of 10? 1, because it's got 1, 0. What's the log of 1? 0. By the way, this is 10 raised to the 0th power. It's a little odd, but it's 1. Okay, and the log of that number is 0. Okay, because you raise 10 to the 0th power, you get 1. There's 0 zeros out of it. So the log of 10 to 0 is 1. What's the log of 1/10, or 10 to the negative 1? No, what's the log of this? Negative 1. Just count the number of zeros. Okay? In this case, you've got negative 1, 0, because you go the other direction. In this one, 10 to the negative 2, the log of 10 to the negative 2 is negative 2. Well, you can do it this way. You can go, well, it's actually how many digits over to 1 in this case. Okay, 1, 2 in this case. 10 to the negative 3. So you get it. So if I said, what's the log of 10 to the negative 14th, what would you say? Negative 14. Okay, we get it. That's not hard. Okay, that's what a logarithm is. Okay? And other logarithmic scales, there's one other big one you've all heard about. Anybody know what it is? I've been expecting one in Djibouti because I read about them happening relatively frequently in Djibouti, but it hasn't happened yet. Earthquakes, right? Supposedly Djibouti has earthquakes, and I'm kind of like, woo, let's get one, but no earthquakes yet. The Richter scale is how you measure earthquakes, and the Richter scale is a logarithmic scale. And you'll notice that logarithms 2 to 3 is 10 times, goes back to that power of 10 thing we talked about. When the log is 2 and then the log is 3, that's 10 times more powerful, right? You ever notice when they're like, oh, there's a magnitude 5 earthquake in California or whatever, you're like, magnitude 5. And then they're like, oh, magnitude 6 earthquake. And you're like, oh, now we're talking a little bit, right? But it's only 1 digit more, but it's 10 times more, whatever the I don't know, shaking is, not exactly. Right? But if you go to like magnitude 8, you're like, oh boy, now people are like really dying and buildings are falling down. Magnitude 9, like the whole city's like wiped out. Right? That one that happened in Japan a couple years ago, magnitude 9, big deal because it was a huge, I don't even know if it was a 9. It might have been 8.3 or something, but it was a big deal because it was really strong. And you only went from going from a magnitude 6, where you're like, whoa, that's shaking a little bit, to magnitude 8, huge deal. It's like 100 times more powerful in general terms. Okay. You were in Japan for that? Wow. Where did you feel it?
I pushed our ship out to sea.
You pushed your. My dad was on a ship when they had an earthquake. He didn't feel it at all. It wasn't a big earthquake, but yeah. Okay. All right. So back to pH. So pH is this negative log of the hydronium concentration. Okay. Let's look at the pH of acidic water, or something that's an acid in solution. Well, acids have a pH that's actually low, below 7. So water, by the way, the pH of water, H2O, pH is 7. Okay, so just get that right now. And the reason is because you take the, well, it was on the last little slide. I kind of, 2 slides ago, kind of went over it. Turns out the hydronium concentration is 10 to the negative 7th. Remember, we said, I can go back one more. Remember we said that the total concentration of hydroniums and hydroxides, 10 to the negative 14th? Well, the hydroniums are half that, 10 to the negative 7 in water, because it's equal amounts, roughly, of, well, exactly, of hydroniums and of hydroxides, yeah. So if you take the negative log of 10 to the negative 7, what's the log of negative 10 to the negative 7? Minus 7. What's negative 7? 7, so that's why the pH is 7. Okay, so you guys can do this. This is not hard math, right? Okay, it's actually pretty easy. Okay, but if you look at acidic solutions, well, acidic solutions have a higher amount or have more hydroniums. Okay, why do they have more hydroniums? Because the acid's donating more protons to those H2Os, so you get H3O pluses, you got more hydroniums. Well, what's a bigger number, 10 to the negative 7 or 10 to the negative 5? 10 to the negative 5 is actually a bigger number. It's got less zeros at the end of it and 0.0. So 10 to the negative 5 is 0.00005, right? 1, 2, 3, 4, 5. That's 10 to the negative 5. And then 10 to the negative 7 is 1, 2, 3, 4, 5, 6. Sorry. Thank you. Yeah, it was 1. That's it. Yeah. 10 to the negative 7 is that, which is a smaller number. So if you have a smaller or a larger concentration of hydroniums, you're going to have a smaller amount of the negative. And by the way, the reason they use this log scale, again, is because the concentrations are so small and the differences can change really like a large amount. This log helps out because it's exponential and it works out. So, all right, 10 to the negative 5. What's the log of 10 to the negative 5? Negative 5. Negative 5. What's negative 5? 5. So the pH of an acidic solution could be 5. Okay, do we get why now? Now you kind of see how the math works out, why pHs, their acids, are lower. Okay? Acids have more hydronium and less hydroxide. Well, the next slide is going to be like the exact same thing except for bases. Bases, you have less hydronium. In fact, you have more hydroxide. So you have less hydronium. Excuse me. So 10 to the negative 9, let's say. Okay, yeah, log of 10 to the negative 9 is negative 9. Negative 9 gives you 9 for the pH. Okay, so a basic solution which has fewer hydroniums ends up with a pH greater than 7. Whew. Okay, kind of interesting stuff. At least when you're trying to think, oh, now I know what pH means. Okay, do you have a question, Ed? No. Okay. All right, that's how that works. Okay. All right. So here's the pH scale itself. This is a little hard to see. But going up and down here, right in the middle, pure water, for various definitions of pure, but pure water, pH of 7, it's neutral. Okay? As you start going up, you get saliva and milk and rainwater and urine and coffee and tomato juice. Pretty acidic stuff, actually, when it comes down to it. pH of about 4, relatively acidic, right? Beer, pH of 3. I never really think of beer as being acidic, but I guess it is.
Well, alcohol's more of a detergent, isn't it, than a...
Is alcohol a detergent? I've never heard of alcohol being a detergent.
I was told that because you mentioned the acid reflux earlier.
Uh-huh.
And I was told that the alcohol acts like a detergent on your...
I'm not sure acid acts as a detergent on your esophagus. It probably... I'm not sure what it's doing, but I have not heard that before. I'll have to look it up. Okay, so go up a little higher. Soft drinks, like anything carbonated. So carbon dioxide is actually an acidic solution when it goes into solution, right? Vinegar, lemon juice, battery acid, right, which a lot of times is sulfuric acid. Okay, and then concentrated hydrochloric acid. By the way, you can get up into the you can have pHs of negative numbers, right? Because what's the concentration of, or what's the log, I should say, of 10 to the 1? 1. What's negative 1? This is negative 1, right? So you can have that for strong acids. You can have a negative pH. Okay? You really don't want to be fooling around with negative pH acids because they're probably very corrosive and not good for you. Okay? Going the other direction, okay, blood, seawater, slightly basic. Okay, baking soda, we know that's basic. Soap is very basic. Okay, ammonia, hair remover. Hair remover? Was that Nair? Remember that stuff? I don't even know if they even sell it anymore. And then oven cleaner. I don't know if you knew your oven cleaner is not an acid. It's actually a very basic solution when you spray it in there. Okay, basic solution. That pH of like 13, pretty high. Okay, so that's the pH scale. All right, tell you what, let's take a break right now, and then we'll come back in about 10 minutes. Hopefully we won't get stuck in colors. When are you going to make it to the lab? I emailed you.
Soon.
Oh, okay. It's got to be before class ends. Okay. We good? All right. All right. So the next little topic we're going to talk about, actually, Andy brought up earlier, which is acid rain. Okay. So it turns out that rainwater is actually naturally acidic. And here's why. Water in the atmosphere is not just water, right? Water vapor. Okay, there's also obviously air in the. Oh, there you go. Are you is it melting? Do it on the other side. Put the lime juice on the other side. You'll see it melt through your styrofoam. Trust me, we'll do it. It's pretty quick. No? Is it doing it? Yeah, it's melting right through. All right. So anyway, acid rain. So acid rain is acidic because there's carbon dioxide in the atmosphere. Okay? And carbon dioxide and water, okay, react together, okay, to produce carbonic acid, which is H2CO3. Okay, this little AQ here means aqueous, means it's in a kind of a liquid solution. Okay? In solution. All right? So the carbonic acid actually lowers the pH, as you might imagine. Okay, because it's acidic, it lowers the pH from 7 to about 5.6. Not terrible. When you get hit by a raindrop, you don't go, oh my, that's hurting me, right? Although if you stare into the raindrops, you might be able to feel a little bit of acidicness on your eyeball or something like that. Maybe you could taste it or whatever. But it's not bad, not terrible for you. It's 5.6, whatever. Okay. Sometimes, however, you get what's called acid rain, which has a pH of less than 5. Okay, which happens when you have all these extra pollutants in the air. And okay, that's why acid rain we talk about comes from pollutants in the air, because when you have things like sulfur dioxide, okay, that actually reacts with oxygen to create sulfur trioxide. Okay, sulfur trioxide reacts with water to create sulfuric acid. Okay, sulfuric acid we know is a strong acid. Okay, so if you get sulfuric acid in the atmosphere, you're going to end up with rain that has a fairly low, in fact much lower pH than is actually normal, what we call normal. Okay, it comes from these pollutants. All right, so that's how you end up with this acid rain. Andy, to answer your question, why don't you get basic rain or base rain or whatever? Well, acid rain is already acidic to begin with, a little bit, but also the pollutants happen to be causing extra acid. They don't cause extra bases. Okay, so if somehow you got pollutants that were basic, well, maybe you'd go the other way, but I don't think that happens on a normal basis. Ah, good question. When a volcano, a good point. When a volcano erupts, you get lots of ash, and that may cause basic solution. Yeah, in fact, I think I've heard about that before, where you get ash and the ash ends up in a lake and it kills all the fish because it just makes the lake too basic. Good point. Hadn't thought about that. Okay. All right. Well, when acid rain actually falls in a lake, okay? Sometimes the lake beds are made out of things like limestone or calcite or calcium carbonate, right? Which are actually basic solutions, or they're bases, right? So if you get a little bit more acid in there and it goes into the water, well, it reacts with the bottom of the lake, okay? And you end up producing a little calcium, right? You end up producing a calcium and some carbon dioxide, and therefore the lake doesn't really turn more acidic. because you've got that extra little buffer, we call it, in there to stop it from becoming more acidic. If, however, you have a lake that is, let's say, granite or some other rock, okay, we'll talk about granite on Monday, right? If it's some other rock, okay, well, you end up with the acid rain hitting the water, making it more acidic, and there's no way for that acid to actually turn into salt or whatever, and so you end up with more hydroniums, and you end up with a more acidic lake, and fish die, and it causes bad things. So, okay, yeah, lots of lakes in New England are rock-based on the bed, and so they ended up with lots of like dead fish and stuff when acid rain was more of a problem in like the 80s. Yeah.
How far can that like spread out? Because I know I would just imagine industrial areas where there's going to be more pollutants, so it produces more acidic rain. But how much does that stay in that immediate area? Or
Yeah, that's a good question. The question is, does acid rain stay in the area where the pollutants are? In fact, it doesn't. So like New England, which has all these poor lakes that got hurt by the acid rain, New England doesn't have, there's not that much pollutants up there. There's not that many people. But if you go down to New York or you go down to Massachusetts or something where there's lots of factories, well, the pollutants go into the atmosphere, go over New England, and then drop their acid rain there. So it kind of harms other people more than just around you. So yeah, not so great. The one story about this kind of slightly different, but when I grew up in right near Syracuse, New York, central New York, and there was a lake there it's called Onondaga Lake, and it was one of the most polluted lakes in the world because there were 2 factories like on the lake, or at least 2 factories that just dumped stuff in there, like mercury and all this stuff, and all these pollutants into the lake. And one of them happened to be the Arm & Hammer baking soda factory. Okay, the baking soda, and they would dump all this extra like baking soda in there, which is a very basic solution, right? And one of the things about baking soda, you guys probably know, you put a thing of baking soda in your fridge and you open it up. You know why you do that? It keeps the odors out because it absorbs whatever volatile chemicals are in the air, and it makes so it doesn't smell. Well, the baking soda factory in like the mid-90s closed, and they stopped dumping all this baking soda in there, and then the lake all of a sudden started smelling terrible. So it's pretty bad news. But they actually, yeah, I know, no kidding. It wasn't smelling so bad because they were dumping all this stuff in there. But what's that?
I thought wherever they have toxic in New York,
they send to New Jersey. Yeah, they probably that's the joke. Yeah. Upstate New York, central New York. Yeah. Yep. So anyway, that's what happens with ocean acid rains. Acid rain for the lakes is worse than the ocean for a number of reasons. I mean, number one, the ocean's huge. Okay, the ocean pH is actually basic. It's actually about 8.2 in the ocean. What happens is the carbon dioxide that's actually in the lake is what makes it basic, or in the ocean is what it gets absorbed. Okay, and that becomes calcium. That actually reacts with the carbon dioxide reacts with the water, producing H2CO3, carbonic acid. That acid reacts with calcium carbonate, which is also in the water, and that deposits on the ocean floor. So a lot of the carbon dioxide and so forth comes out of the air and is deposited kind of at the bottom of the ocean, and that doesn't really get as affected by acid rain because of the scale of the whole thing. Okay, so ocean actually captures a lot of the carbon dioxide in the air from pollutants and from other issues. Okay, so I guess it's not as much about acid rain as about pollutants in general, like carbon dioxide. Okay, so they say the oceans are actually, the pH is changing a bit, but the oceans are really what keeps a lot of the carbon dioxide from becoming greenhouse gases, and so forth. Okay, all right. So that was acids and bases. Okay, and remember, acids and bases reactions are all about protons. Okay, you're either accepting or donating protons. Okay, we've got this other kind of reaction called oxidation reduction reactions. Okay, you've probably heard of oxidation before. Okay, I think Tom actually mentioned a couple weeks ago when he said, "Are we ever going to talk about rust?" Exactly. And we are going to talk about rust, and that's an actual oxidation reaction, which we'll get to. Oxidation is all about the transfer of electrons. Okay? Before we're talking about protons, now we're going to talk about electrons. And here's an example. Okay? If you have two sodiums, okay, and they become positive sodium ions, well, they don't gain protons like they might in as a base. They actually lose the electrons. Okay? It's not like a transfer of protons here. It's a transfer of the electrons. So in this case, you've got two electrons which have been separated, and that's called oxidation. So oxidation is when you lose an electron. Well, guess what? Reduction is when you're gaining electrons. So you start out with chlorine gas, let's say, gain some electrons, 2 electrons, and you end up with 2 chlorine minus ions. Okay? Because electrons actually, in this case, transfer from the sodium. If you're talking about sodium chloride, transfer from the sodium to the chloride. Okay? All right, well, guess what? We have another little phrase we can use. I'll write it down over here. Did before. For oxidation and reduction, we have this fun little phrase that's Leo the lion, L-E-O, Leo the lion went Ger, G-E-R. I don't know why it's G-E-R. Well, I do know why it's G-E-R. Because this stands for losing electrons is oxidation. Gaining electrons is reduction. Okay, so I'll leave this up here. Okay, so now we'll be able to go, okay, so if you lose electrons, you're going to be oxidized. If you are gaining electrons, you're going to be reduced. Okay, that's what oxidation and reduction. And by the way, we call these types of equations redox equations for reduction oxidation. Okay, all right. So if we're talking about gaining oxidation and reduction, here's a little chart that shows you what's happening when you're doing this. You can either lose electrons, which is what we just said, for oxidation, or you can think of it as if you're gaining oxygen. And we'll talk about why that's the case in a little bit. Okay? Or losing hydrogen. Now, losing hydrogen sounds like an acid base. Well, it kind of is. So really, you're not going to worry too much about this one. But it's in solutions. It's in cases where you're not really in solution anymore. We're not talking about solutions anymore. We're talking about this other form of equation or other form of reaction. Okay, so the big one is losing electrons, oxidation, also gaining oxygen, which we'll see what that means in a minute. And reduction is the exact opposite, where you gain electrons or you lose oxygen, okay, or you gain this hydrogen, okay, which again sounds like protons and bases, but it's in a different sort of situation. But we're not going to worry about these ones as much. Okay? All right. So, a little check question for you. What element within the reactants here is oxidized in the following equation, and what element is reduced? So let's take a look. Iodine 2, which is diatomic iodine, plus 2 bromine ions, which happen to be negative, you end up with 2 iodine ions, which are negative, and 2 diatomic bromine gases. Okay, so what's happening here? Leo the lion went Ger. Losing electrons is oxidation. So which one of these had to lose electrons? And if you lost, remember, electrons are positive or negative?
Negative.
Electrons are negative. So if you're losing the electrons, you're becoming more positive. So which one here loses the electrons and becomes more positive?
Bromine.
Bromine. So that must have been Leo, L-E-O. Must have been oxidized or reduced. It lost its electrons, so it becomes oxidized. So bromine is oxidized. So it's either this one or this one. Okay? Okay? Sorry? Okay, so now let's look at the other one. So the iodine, it becomes negative, meaning it's gaining the electrons. G-E-R. Gaining electrons is which? Reduced or oxidized? Reduced, right? So that's got to be this one. So we hope that it's B. Okay? All right, there we go. This is the kind of thing that I will ask you on your exam. Okay. All right. Iodine is reduced while bromine is oxidized. Okay. All right. Wasn't too hard. Okay. All right. Now we get into some fun stuff here. Remember how we talked about ion flow being current flow, right? Ions are just electron or charged particles. That means that electrons are involved. And if you have ions in solution, you can actually get a current to flow, which means you can create electricity chemically. And every one of you has used electricity created chemically. You use it all the time, right? I'm using it right now when I unplug my computer, right? Because there's a battery in here, and that battery is made of lithium and a bunch of other things, and it's a chemical reaction that actually makes the battery produce an electric current. Yeah?
So it's like the same concept with like the clocks that you can run off a lemon or a potato.
Exactly. In fact, I have a lemon clock somebody sent me. I don't know why, but they sent me it in the mail, which was kind of fun. But I haven't used it yet. So maybe I'll bring it in tomorrow and we'll make a little lemon clock. All right? So in this case, this is what we've got here. We've got a nail, an iron nail. Okay? Fe is iron. Okay? An iron nail. And it is in, I'm not sure what it's in actually. It might be in water in this case. Does it say water in the, I think it might be water. And in the other, does it say water? Yeah. In the book, yeah. And in the other one, we have a penny. Okay, a penny happens to have copper, also some zinc in it. Okay, and I guess this is in some sort of chloride solution. Okay, and what will happen is in the solution here, you're going to actually get this reduction and oxidation happening. Okay, if you're getting Fe2 pluses, you're losing electrons. So this side's doing what?
Reduction.
Leo, losing electrons is oxidation. Just look. You need to, right? I always do. I don't remember it off the top of my head. Right? So this side's reducing, and this side's producing chlorine minuses, which means it's gaining electrons, which means it's going to be reducing. Okay? Now, what's going on here? Is the light bulb lit? No, and it's not just because they messed up and forgot to light the light bulb, right? You can see here, electrons should flow through here to here, right? Because they're being created in these solutions, and there's more positives over here, so it should end up pushing electrons this way. And there's more negatives over here, so it should end up. Sorry, it's the other way around. There's electrons that should be flowing out this way into here. Well, it's not happening. Well, we've got to switch the case a little bit. What did we know about circuits from electricity class? They need to be a complete circuit, okay? Right now we don't have a complete circuit here. There's no way to go back to the other thing. So what you do is you create this little, what we call salt bridge, okay? And so if you did this experiment, you could actually, if you had this little tube here, and you put salt water in it. In this case, they put sodium nitrate solution in it. And they have a little semi-permeable little stoppers on here. What that means is that you can get a little exchange between the two. It's not fixed, like it's not like closed off. You can get a little exchange in here. And what's happening is that little exchange doesn't make it so that this solution drips out. It stays in there, but there's enough of a permeability there that it allows the electrons to go through. So what happens is you can get electrons now going through the whole system because this little salt bridge. Okay? All right. So you end up with a situation where you've got the electrons now flowing through, and you've got a chemical reaction that produces current. Aha, chemical electricity in that sense. Okay, kind of cool. Kind of cool stuff. Right? Yeah, question?
Is it going to be a visible reaction too? Like, is the nail going to decompose?
The nail is going to decompose. I mean, you'll over time you'll see the excuse me, you'll see the nail actually being being corroded away, oxidized, right? And by the way, rust, like we'll say, you'll see it rust, because this is a rusting sort of situation here. It's being oxidized, yeah. And this won't go on forever. Eventually, both the iron and the copper will dissolve away, or basically dissolve into solution. It'll be dissolved away. Okay. All right.
Dissimilar metals.
They are dissimilar metals, yes. And it's also two different types of solutions too. Okay. So that's the basis for a battery, actually. Okay. In your book, they show you this kind of cutaway picture of a battery here. What the battery itself, okay, if you look at a battery, it's got a couple different things going on here. You've got a graphite rod in here, and graphite's a very good conductor of electricity, okay? The graphite rod is in the middle there. Then you've got this paste, which is made up of, what is that? Nitrate and chloride, and zinc chloride, and magnesium oxide, and it's this like pasty stuff. Okay? And then you've got a nice membrane out there to kind of keep it all together. Okay? And you have a reaction here, a reduction and oxidation reaction. And the outside is zinc. The outside of the inside of the battery is made of zinc. Okay? And what's happening is the ammonia, or well, I guess this is the nitrate, is reacting to form ammonia and hydrogen, two gases, by the way. Okay? And the zinc is an oxidation reaction. Okay? It is losing electrons and becoming zinc 2+, and it loses those electrons. Those electrons now can flow through to light the battery. And that's how you've got this electric current forming. Well, problem is when you have gases like ammonia and hydrogen, you don't want those to get released into the atmosphere. That's really what the rest of this paste is for. You get reactions which which react with those gases to make it so they don't blow up or leave the battery. Okay? So that's kind of how a battery works. Okay? And I'm going to show you a little video on batteries. This is by a guy called the Engineer Guy, who does a whole bunch of videos. If you'll see it, you can see them online. They're actually pretty cool videos that he. I think this is the one right here. How a lead-acid battery works. Okay. Could you hit those lights? And Eric, you want to hit those lights?
Is that his given name?
His given name is not the Engineer Guy, but that's what he calls himself for these videos. Okay. All right. He's going to talk about lead-acid batteries, actually.
The increasing amount of technology we rely on in everyday life makes portable energy sources essential to our world today. We can power our cell phones and laptops with lithium-ion batteries, run flashlights from alkaline ones, and many of our watches depend on batteries constructed with silver oxide. This one, though, may be the most important of them all. Now, I know it seems a clunky, old-fashioned thing. It was invented in the 19th century, but it still makes our world move by starting our cars, motorcycles, and trucks. No wonder it's the best-selling battery. If you understand how this battery operates, you can grasp the principles underlying any of the newer ones and even see why no single type of battery can be used in all applications. Let's take a look inside. The first thing to note about this motorcycle battery is that it's heavy. That's because it's tightly packed with lead and lead oxide sheets, both of which are very dense. This is a cell from an identical battery, and you can see the lead, and underneath this, the lead oxide. They alternate throughout the interior. So let me show you how they store electricity using just two plates. So I have here a lead plate and a lead oxide plate from the battery, and the sulfuric acid. And now watch what happens when I connect the leads. The LED lights up. A current flows from the lead oxide cathode to the lead anode. The lead gives up electrons which the lead oxide accepts. This exchange turns both plates into solid lead sulfate. Now, let me measure the voltage difference between the two leads. And you can see that it's about 2 volts, which means that To make this 12-volt battery, 6 cells are linked in series to make up the 12 volts. So that's the basic electrochemical reaction. Now let's look at how you engineer a battery. We want a battery to have a high density of either energy or power, and that difference being that batteries with a high energy density can store large amounts of energy and release it reliably over long periods of time, whereas batteries with a high power density release large amounts of energy quickly. This battery was designed with power in mind because we need a burst of nearly 400 amps to start a motorcycle. To save space, we need to pack the plates in here tightly, but in order to ensure that the electron transfer takes place through the terminals, the plates are mechanically separated by these permeable layers. Now, let me show you 2 plates from a discharged battery so you can see the effect of a deep discharge of a battery. If we look at these 2 plates, we can see the effect of a long-term discharge. This light coating here is lead sulfate. That explains why if you run a car battery to 0 charge a few times, you're likely to kill it. As the battery discharges, lead sulfate cakes the space between the plates. If too much builds up, you'll never be able to recharge the battery. This highlights how every different application needs a different type of battery. You see, with most engineered objects, there are going to be trade-offs, giving away some characteristics you want to gain others that you must have. Indeed, the toughest part of engineering often ends up being balancing the trade-offs in a design. For example, a car battery does a great job starting a vehicle, but not running one, like an electric car. Nor is it a good candidate to store energy from solar panels on a house. There we harvest energy from the sun, charge up the batteries, and then use the stored energy in a variety of ways until the batteries die, and then recharge them with the sun's energy. For this use, you would use what is called a deep cycle battery. As the name implies, this battery's capacity can be largely used and then recharged easily. To convert an SLI battery, like used to start a motorcycle or a car, into a deep cycle battery, we do 3 things. We use thicker electrodes to increase energy density, space them further apart so lead sulfate debris can fall off of them, and add room below where that debris can accumulate. The trade-off is that it's larger, heavier, and gives off a lower current than a car battery. It would seem that we'd want to get rid of the lead-acid battery. It poses a significant environmental risk if disposed of improperly. We still have the 19th century lead-acid battery because of what nature has handed us. Plentiful electrode materials, lead and lead oxide, both very high in conductivity. Once we arrange these materials correctly, we have a cheap battery with a high power density. No other materials found in nature meet these criteria so well, which means that with current technology, it is extremely difficult to overcome this barrier. That's why 19th century technology is still the go-to for starting our cars. I'm Bill Hammack, the Engineer Guy. This video is based on a chapter in the book, 8 Amazing Engineering Stories. The chapter features more information about this subject. Learn more about the book at the address below.
Should give me money for promoting his book. Yeah, so you think, hey, why are we using those old clunky lead-acid batteries? But you know, they're pretty good for what they do, and we don't have another technology that really works better at the moment. So, yeah, I mean, they're working on it. Honestly, one of the reasons we don't have, like, for instance, electric cars everywhere is because battery technology just isn't good enough yet. There's things called supercapacitors, which also store charge like a battery, but they do it without chemicals. They do it with what's called a capacitor, where you charge up 2 different plates that hold the charge between them. But they're not quite as much, they don't work as well as just the plain old lead-acid battery. Yeah. Now, the batteries that you have in your, like a Prius, not lead acid. They are like nickel chromium or something like that, but it's because you need to charge them up and discharge them all the time. And as you saw in there, if you do that too much for your battery in your car, you're going to kill the battery. Yeah.
Yeah, well, the car actually runs off of your alternator. It doesn't actually run off the battery all the time.
The car, well, okay, yeah, the car itself doesn't run off your alternator so much as the electricity in your car, like the electric components in your car run off the, yeah. The car itself runs off the engine, right? But the electric components, like the lights and the radio and the, you know, whatever else you got in there, car lighter and whatever, work on mainly off the alternator. Yeah, the battery, the good news about batteries in your car, the alternator can die for a while and the battery will be fine for a while. But, you know, you don't want to kill your battery. You don't want to kill your battery completely because of what he said.
When there's an axe murder after you.
Exactly. So there are other ways of producing electricity using chemicals through things called fuel cells. Okay, and the book claims the fuel cells are like the wave of the future, right? Fuel cells are kind of cool. You've got basically oxygen and hydrogen and water. Okay, basically oxygen in one side and hydrogen in the other. And when oxygen and hydrogen combine together, you get a lot of energy. Okay, and you get this reaction here, which will produce water vapor. No big deal with water vapor. That's actually not bad. Okay, and it'll also produce oxygen. Also not bad, right? If it's not the part that just doesn't react. Okay, so you end up with a situation where you've got no pollutants into the atmosphere with this fuel cell. Okay, so you say to yourself, well, oxygen's in the atmosphere. That's great. Why don't we can use that. That's pretty easy. Hydrogen, all right, there's some hydrogen in the atmosphere, but we need to get the hydrogen into elemental gaseous hydrogen, right? Well, the problem is that for the amount of hydrogen to run your car, it's like a huge amount of hydrogen, right? And you need to compress it down, and that compression is really, really hard to do and takes energy to do it. So it's a trade-off there. So we'll see. Yeah, Tom.
BMW actually had one that they were bringing around to schools around the country. It actually came by the Naval Academy.
Oh yeah, BMW.
Yeah.
Had yeah, I believe it. The Governator, Arnold Schwarzenegger, actually had, I think it was General Motors or something, produced a Humvee that was hydrogen based. Cost them like $1 million to produce, but they got a lot of press out of it. Someday, you never know, we may have hydrogen cars driving around all over the place, but the storage and production of the hydrogen is still tricky right now. Okay. However, there is a way to produce hydrogen fairly readily using electricity. Okay. What you can do is you can do this thing called electrolysis. Okay. Electrolysis is the use of electric energy to produce a chemical charge. That should say charge, not change. Okay, a chemical, well, actually, no, I'm sorry, it is a chemical change, not a chemical charge. It's electrolysis is the use of electrical energy to produce a chemical change. Okay, what's happening is you're taking the two leads of a battery, and if you put them, for instance, in water, okay, the current that goes through the water actually separates the oxygen from the hydrogen in the water, and you get hydrogen gas and oxygen gas, which is pretty cool. Okay? You actually get more hydrogen gas than oxygen because there's twice as many hydrogens as there are oxygens in water. And you can do this. Now, I wanted to set this all up. I didn't have any epoxy. I wanted to set it up with 2 water bottles. I may try to do it for tomorrow. But I didn't have any epoxy, which I wanted to put the 2 bottles together. I couldn't find any at the exchange. They just have super glue, and super glue doesn't work so well on like plastic bottles. So for what it's worth, I might try to do it tomorrow. But I'm going to show you another little video here in a second that deals with electrolysis of. Actually, I'm going to show you 2 videos. One is electrolysis for producing hydrogen and oxygen. It's kind of cool. And the other one is electrolysis to produce aluminum. Aluminum, as it turns out, is actually pretty hard to produce. It takes a lot of electricity because they use this electrolysis to produce it. And they do it in these giant plants to make it happen. Have you guys ever seen the show How It's Made? Great show. All like 5-minute clips on how all this cool stuff is made. Gummy bears. They show how gummy bears are cool when they make gummy bears, right? Gummy bears are cool. They have one that shows how chains are made. I never thought I'd be so interested in how a chain is made, but it's cool. I mean, it's kind of hard to get those little links. Like you got to make the links and you got to bend them, then you got to link them together, and all has to happen at like really high temperatures. It's cool. Anyway, I'll show you the one on this. So let me first show you the video on electrolysis to produce hydrogen and oxygen from water with electricity. Okay, so let me find that one. The one on, I have not seen the one on fleece.
They did the Fuller Tech factory, and most fleece is made out of recycled plastic bottles.
Most fleece is made out of recycled plastic bottles. I can understand that. can understand that. That's cool. Okay, Eric, you want to hit the lights again? All right. This is this guy's a little crazy, but here it goes. We like these guys sometimes. This is on electrolysis.
I have here a 9-volt battery. This is going to serve as a source of direct current for a little electrolysis demonstration I'm about to do for you here right now. And once again, the purpose of electrolysis is simply this: to decompose compounds into their elements. As you know, synthesis reactions tend to be spontaneous. In other words, once you get it started, they continue on their own until they're done.
By the way, he talks about a couple of different types of reactions. Don't worry about the details of that. But he talks about these.
However, decomposition reactions require the continuous input of energy, such as the energy from a DC power supply. This is the negative terminal of our 9-volt battery.
By the way, he's got this on a video camera, so he's got the video camera shooting right into this little cup of the solution that he's got. This is just a regular old 9-volt battery that you have in whatever components you got. Okay.
This is the positive terminal of our 9-volt battery. Now, electrons are coming out of the negative end, and electrons will go in to the positive end. So that means that this end of the battery can give electrons to a species that needs to undergo reduction. And this can pull electrons away from any species that will undergo oxidation. Now, the first thing we're going to do is the decomposition of water. H2O forms H2 plus O2, balance that out. And H's plus becomes 0, so the H plus 1 will undergo reduction as its charge reduces. The O is minus 2, it ends up as 0, so its charge increases, oxidation, as those 2 electrons are pulled off. So let's try this. Let's see if this battery can put out enough juice to split this water up into hydrogen and oxygen. Now, they're both gases, so the outcome should be fairly predictable. We now have water in this beaker, and you'll notice that there's absolutely nothing going on. We would expect, if this was decomposing, that we'd get some hydrogen and oxygen gas bubbles coming off of the terminals. Aha! But remember, water alone does not conduct electricity. It requires the addition of an electrolyte. Now, what electrolyte can we add that won't interfere with this? Well, we could try salt, because salt would allow us to conduct electricity, but salt does something interesting we'll get to a little later in this video. What we're going to do is we're going to add something that is an electrolyte and has hydrogen in it. Can you think of anything? How about an acid? Specifically, sulfuric acid, because the sulfate ion will not decompose under the application of electricity. Johnny was a chemist. Johnny is no more. What Johnny thought was H2O was H2SO4. As we add the sulfuric acid to this, well now, all of a sudden we're getting electrolysis. How about that, huh? So what's happening here? Simply this. Any H plus that happens to be in the vicinity of this terminal of the battery would be force-fed electrons coming off that end, turning into hydrogen gas. Now, as you know, hydrogen is diatomic when it's not in the compound, Brinkelhoff. So we have to balance the Brinkelhoff in that half reaction. Over on this side, any O-2s that happen to be in this vicinity, O-2, are going to have those 2 electrons stripped violently away. But as you know, when oxygen is not in the compound, it's diatomic. So we have to balance for Brinkelhoff in that reaction. Now, if we're going to double this, we need to also double that. So those 2 electrons are actually 4 electrons, right? 2 for each of the oxygens. Now, the formula is H2O, so we should expect to get double the amount of hydrogen as we're getting oxygen. If you take a look at the size of the bubbles coming off the hydrogen electrode, they're not such of a much, but look at the size of these monster bubbles coming off the hydrogen electrode. They're huge! 2-to-1 ratio of hydrogen to oxygen. What we could do to track the gas is actually invert test tubes that have been filled with water. And as the gas goes up, it pushes the water down filling the tube with gas, in this case, hydrogen gas. How much oxygen would you get? Well, half as much. Half as much oxygen would be trapped as hydrogen. And that's the electrolysis of water, splitting apart, decomposing a compound by adding electrical current. So what if instead of using...
By the way, if you put a flame to that hydrogen, it would explode. Put a flame in the oxygen part, it would actually glow a little more, but the hydrogen one would explode.
Using sulfuric acid as our electrolyte, what if we had used a salt like sodium chloride as an electrolyte? Well, there you run into a slight problem, and I'll show you what I mean. We could use salt, and it will allow this to conduct electricity, but look what happens when we put sodium chloride in with water to make it conduct electricity. There goes the salt. And I'm going to add a few drops of some special ingredient to this. Some phenolphthalein. The reason behind this will become apparent in just a moment. Okay, let's add some water to this mix. Sorry about the noise, there's some heavy construction going on in another room. So what's happening here is simply this. We are getting hydrogen gas bubbling off of this, but we're really not getting much going on over here. There's not really a lot of bubbling going on here. Also, notice that this has turned pink. Why would it turn pink? Hydrogen's not a base. Phenolphthalein only turns pink in a base. So what's going on here? Well, here's the thing. You're not just getting hydrogen here. You put salt in, and when you put sodium chloride in water, it ionizes to form Na+ and Cl-. Now, this being, again, the negative terminal, the Na+ is going to be attracted to it. And at that terminal, the Na+ will pick up the electrons that the battery is giving off and turn into pure sodium. Hey, that's wonderful. Now we can make some sodium. Except, you might remember, sodium is an alkali metal. And the instant it touches, what else do we have in here? Water! As soon as the Na touches the water, it immediately turns into sodium hydroxide, which, as you know, is a base. That's why they call metals like sodium alkali metals, because alkali means basic. So what are we forming over here? Well, apparently not a whole heck of a lot. We are getting some bubbling going on here, but it doesn't appear to be coming much from the terminal. Let's see if we can figure out what's going on here. Well, if the sodium's attracted here, then guess what's attracted here? You got it. The chlorine. Now chlorine, when it oxidizes, Cl- forms Cl2 0 plus 2 electrons. Okay, chlorine is a halogen, and halogens are extremely corrosive. So we might actually be doing some damage to this terminal. As soon as the chlorine forms, it should attack the metal of this terminal and just go crazy. I'm chlorine, I'm gonna eat you up. Okay, we're gonna make a fresh start with the fresh battery. Once again, this flared end, that is the negative end, and the round end, that's the positive end. I'm going to use a different salt this time. This time I'm going to use a salt that's going to give us a visible product. I'm going to use potassium iodide. Potassium iodide. Here it goes. All right, there we go, some potassium iodide. Well, as you can see, we're definitely getting hydrogen bubbles, a whole lot of them coming off here. But there's something else coming off of this terminal right here, this yellowish brown goop. What the heck could this possibly be? Oh, that's just wrong. Look at that, it's just brown and yuck. What could that possibly be? Well, that's easy enough to find out. See, what's happening here is, yeah, we're decomposing water. We're actually getting some bubbles coming off here, some bubbles of oxygen. Plenty of hydrogen, just a little bit of oxygen. So what else is coming off here? Apparently oxygen is not the only thing that this terminal is giving off. Well, we dissolve potassium iodide. And potassium iodide, when you put it in water, ionizes to form potassium ions and iodide ions. So the potassium ions, just as before, get attracted to the negative electrode where they pick up the electrons and form potassium, which immediately reacts with the water to form KOH, potassium hydroxide. We'll prove that in just a moment. So what the heck is this orange stuff? Well, yeah, the O might be going here, but so is the iodide. The iodide is going there. I-1 is actually going to be stripped of its electrons by the battery to form I0. The electrons go. Iodine, as you know, is diatomic, Brinklehall, so we have to balance it. So this brown, this reddish brown stuff, this whatever this is, that's iodine. Now, iodine is not water soluble. You might remember that the iodine molecule is non-polar, so it's not going to dissolve in the water. So we're actually getting microscopic precipitate here. Oh, look, all sorts of stuff is happening. Look at all that stuff floating around. And, oh, man, I'll bet you that's pieces from the inside of the battery. Remember, don't try this at home. All right, now, to prove that potassium hydroxide is being formed here, as the potassium forms and immediately reacts with the water, we'll add our old friend, phenolphthalein. I didn't want to add it before because it might interfere with this lovely yellow, forget it, I like to interfere with it, I don't like that color. Phenolphthalein, at the ready. Boom! Looky, looky. Isn't that just the gosh darn prettiest thing you've ever seen in your whole life? So that's electrolysis, using electric current to decompose a compound. Because as you know, compounds just ain't gonna decompose on their own.
All right. Compounds aren't going to decompose on their own. So that's how we might produce hydrogen and oxygen from an electric current in your battery. Okay, tell you what, let's take another break right now. Please come back in 10 minutes.
All right,
All right, thanks. Okay, so the next thing I'm going to show you is just a little how it's made video on aluminum, because aluminum uses electrolysis as well, as you can kind of see here. You've got an oxidation reduction reaction where you're bringing in aluminum oxide, which I think is called bauxite, which is what you can mine out of the ground, and it has aluminum in it. So the video talks all about a little bit about aluminum itself and how relatively new it is. The top of the Washington Monument was made of aluminum. In fact, I think it still is, because back when they made it in like the 19th century, aluminum was really expensive, and they figured, well, we're going to make this shiny thing on the top, and it's going to be really expensive, so it's kind of cool. All right, Eric, go and hit those lights again, and you can hit those lights. Tom, thank you. And I will show you this. So about 5 minutes long.
Take a look around, and you'll find this wonder metal everywhere, in everything from screen doors to jet planes. Aluminum has so many applications because it's light and strong, and it's corrosion and crack resistant. Producing aluminum is costly, but it saves money over time. Aluminum, so widely used today, and the world's most abundant metallic element, does not occur in a natural state. The most available source of aluminum is actually bauxite. Bauxite is mainly mined in tropical countries. The aluminum atom in bauxite is bonded to oxygen molecules. These bonds have to be broken by electrolysis to produce pure aluminum. Bauxite is carried by rail to the plant where it will be crushed. Then, through a chemical transformation called the Bayer process, alumina is extracted. This is then roasted in calciners to eliminate all moisture. This is the reduction facility.
Look at how big this facility is. It's amazing.
This plant has 432 pumps through which a powerful electric current will be passed to produce electrolysis. An overhead crane dumps alumina into the pots. Then the electric current from the anode passes through the alumina that we see here at the bottom of the pot. Via the process of aluminum reduction at 1742 degrees, the anodes anodes lose volume and will have to be replaced. It's a continuous operation. Each anode has a lifespan of about 20 days. Spent anodes are recovered from the pot with this overhead crane and carried off to be recycled. They clean the aluminum rods, which will then be reused. Here we see the crust formed atop the anode. When the anodes are replaced, the accumulated impurities have to be recovered from the top of the pots. This is accomplished with these pincers. Then a new anode is inserted into the aluminum and electrolysis continues. The electric current breaks the molecular bonds. The heavier aluminum collects at the bottom of the pot, while the oxygen bound to fluorine is released as a gas, which is drawn off and treated. The liquefied aluminum remains at the bottom of the pot. It has to be recovered in this huge crucible with the tube. The tube is dipped into the bottom of the pot, and a vacuum system draws the molten aluminum from the crucible. The aluminum is recovered in a short time. Air is vacuumed from the crucible by a flexible pipe held by an operator. The tube is finally withdrawn, and the overhead crane dumps another quantity of alumina into the pot. Thus, the aluminum fabrication process continues uninterrupted. The crucibles filled with molten aluminum are transported to the casting house. Their contents are poured into holding furnaces that have a capacity of 60 tons. In these very hot furnaces, the molten aluminum is stored to await casting. Finally, casting begins. The aluminum can be semi-continuously vertically cast, producing ingots, sheets, or billets, or it can be directly cast into semi-finished products. The cooling of aluminum pieces is accelerated by water sprays. The large rectangular ingots, which can weigh up to 25 tons, will head for hot rolling, and eventually will be fabricated into products like aluminum foil. From 4 to 5 tons of bauxite have produced 2 tons of aluminum, which in turn produces 1 ton of aluminum. This particular plant produces 200,000 tons of aluminum annually. Some other facilities can turn out as much as 400,000 tons.
There you go. Kind of cool how they make that stuff. I never knew that it took that much processing to make aluminum. So when you use that aluminum foil, don't forget to recycle your cans. Sorry, question?
So they get 4 tons of bauxite to make 1 ton of
Yeah,
aluminum?
yeah. A lot of things are like that. It takes a lot of materials to make some like small amounts of other material. It's surprising. Rubber, so yeah, it takes a ton. It takes lots and lots to make that. Yeah. So that's electrolysis. Okay, so there's a couple other things: corrosion and combustion, reduction, oxidation. In this case, iron rusts by oxidizing with water. With oxygen, and it produces water and produces Fe2O3, which is rust. Okay, that's what happens. And by the way, when something rusts, it actually gains mass. It goes the iron actually gains oxygen as mass, and so things that are rusted out will be heavier than if they were not rusted, as long as pieces don't fall off because of the rust. Okay. All right. Another electrolysis sort of thing that we see a lot of times is chroming something, right? To put chrome on like a hubcap or something. Okay, battery, you've got solution, you've got like a hubcap in there, you've got chromium, and the chromium comes off, the chrome comes off the chromium electrode, ends up depositing itself on the hubcap, and you get that nice shiny chrome on there. Electrons flow into the hubcap, giving it a negative charge. Positive charged chromium ions, which have been, if they're positively charged, they have been what? Reduced or oxidized?
Oxidized.
Because they've lost electrons, right? Yep. So there you go. Okay. And so that's what you end up getting with that. And then finally, combustion is actually a, whoops, what the heck is going on there? Hang on. I don't know either. There we go. Combustion is an oxidation reduction reaction between some non-molecular, non-metallic material, like wood, for instance, and oxygen. Okay? These type of combustions are normally exothermic, which makes sense because they're nice and hot, and that's why you have a nice warm fire. Okay, they're also self-sustaining, so you start a fire and it continues to burn, as long as you get oxygen and fuel. Okay? All right, so that's those types of reactions. Now, the last thing we're going to talk about for like 40 minutes or so is this organic compounds, otherwise known as organic chemistry. If you were trying to go to medical school, you would have to take organic chemistry class, which is, they call it a weed out class for doctors, because it's a pretty hard class. I took it when I was actually started out as a biomedical engineer in college and took organic chemistry, and it kicked my butt. It's a hard class because there's a lot of, unfortunately, there's a lot of memorizing, but there's also a lot of like three-dimensional kind of thought involved with these chemicals and how they look, and I just wasn't really ready for it. But anyway, I did all right in the end, but had an all-nighter before the final, and it was kind of ugly. If you took an organic chemistry lab, you end up doing the lab. At my school, it was 6 hours long, the lab. So it was a long one. You'd have to like start something going, and then you'd go out and get something to eat and come back, and leave your partner there or whatever. So anyway, organic chemistry. Organic chemistry is this study of compounds that have carbon in them. Okay, so when you think organic chemistry, think carbon. Okay, why do we call it organic? It's not like organic lettuce or whatever, although that has something to do with it. Organic compounds are any members of all these gases, liquids, solids that just contain carbon. Okay? You can have either natural or synthetic organic compounds. It's weird to think of something as being a synthetic organic compound, right? But all that means is you're creating it in a lab. It's still the same carbon-based stuff. It's just created in a lab. And there's hundreds of thousands of organic compounds. Why are there so many? Carbon likes to bond to stuff. Okay? I don't know if you remember, carbon has 4 spots where it can bond. It needs 4 extra electrons. So you can have 4 places to bond, and there's over 13 million known organic compounds. Sorry, there's 100,000 compounds discovered or created each year. Okay, I mean, it's like a huge, huge field. Okay, again, carbon forms strong bonds and has 4 bond locations. Okay, all right, let's start out with the simplest organic compounds, hydrocarbons. Any idea what they're made of? Hydrogen and carbon. Okay, pretty simple. Okay, that's what hydrocarbons are. Okay, we've all heard of hydrocarbons before. Methane is a hydrocarbon. It's just CH4. Very simple stuff. Okay, it's a carbon, 4 hydrogens attached to it. Okay, that's the stuff cows produce when they fart. And so do you sometimes too, right? But that's what it is. It's methane. Okay, it's actually a greenhouse gas, not so great for the environment, but it burns pretty well. So we can use methane for fuels if we need to. You've also got this one, which is an interesting one. It's called octane, which you've all heard. If you've gone and filled your car up at the pump, you can buy 87 octane or 89 octane or 92 octane. It all has to do with basically how straight the molecule is and how even it is there. And you've also got this thing like this one's called polyethylene. Poly meaning many, ethylenes in a row here. The reason they kind of fade this off is because polyethylenes can be really, really long. Okay, if I'm not mistaken, polyethylenes are in things like nylon, which is just really long strings of hydrocarbons. Okay, yeah.
Polyethylene glycol.
Polyethylene glycol. I'm not. It's I think it's a type of alcohol actually, but I'm not really sure much about it.
Antifreeze.
Antifreeze, yeah. Yep. Yep, antifreeze has, it's an alcohol that, we'll get to alcohols in a little bit, but yeah, that's good. Okay. All right, so hydrocarbons. So remember how I said organic chemistry, a lot of times it's about structures and about three-dimensional thinking and so forth. Hydrocarbons can differ in the way carbon atoms connect with each other. They can either be, like we said, the number of carbons and hydrogens, but they can also differ in the actual, the way those hydrocarbons are connected together. This is called N-pentane, and see how it looks like this. You've got the carbon, 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 and then kind of off each end you've got all the hydrogens, right? You've also got isopentane, which looks like this. It's a little weird. It's a different structure. Carbon, 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 and then another carbon stuck off this one. So this carbon in the middle here has a carbon there, and carbon there, all attached to it. And then you could get this where there's one carbon in the middle. This is called neopentane. I'm not going to ask you to memorize any of this stuff. If you were taking a real organic chemistry class, you might have to memorize this stuff. It gets to be a lot of memorizing, right? But there's carbon right in the middle. It's got 4 carbons off of it. All those other carbons have hydrogens off of them, and that's a different form, right? These little stick structures, they just basically show the carbons, okay? So every time there's a little bend, that's a carbon. And then they just don't bother showing you the hydrogens because we always assume the hydrogens are there. Okay, so it's just an easy way. Notice something about this. It's tough to see up here. This is C5H12. This, C5H12. This, C5H12. They've all got 5 carbons and 12 hydrogens, but they're just arranged differently. Okay, we call those different configurations. Okay. They have the same chemical formula. Yeah, okay, they have the same chemical formula. That's interesting. Okay. Of these, you can actually produce lots of different of these configurations. The one we just saw, 3 different configurations. These 3 right here, 3 different configurations. Okay. If you have C6H14, there's 5 configurations. C7H16, 9. C18H18, 18 configurations. Look at this. C20H42, there's 366,319 different ways you can put those together. Right? You do not want to memorize all those. Okay? They all look different, but they're all C20H42. It's all about the arrangement of them. Okay? And in a solution of this stuff, you're going to get all these different types of arrangements. Okay? They're called isomers. Okay? What did we call when you had an atom that had more neutrons? Isotope, right? Iso being it's a different form, like a different form of the same thing. Okay, these are all isomers. Okay. So hydrocarbons, as I said, you've got so you can have configurations like this, different configurations like this, but not only that, you can have different what we call conformations of the same configuration. So this is weird. Look at this little configuration. It's got a carbon there, carbon there, carbon there, right? So it's got 3 carbons there. This one has a carbon there, carbon there, carbon there. But guess what? This one is if you took this bond and you went and twisted it. So really, it's the same exact molecule, okay? But the bond is just twisted in some other different direction. If I showed you this 3-dimensionally, I guess you might be able to see it a little better. I think your book shows some of these in 3 dimensions. But it's basically, not only is it the same structure and the same configuration, but you can twist some of the bonds to be angled in a different way. Whew, it's crazy stuff. Okay. All right. So yeah, here you go. Here's 3 conformations of pentane, right? Which I think is C5H12. Well, yeah, that's the one we did before. You've got the one that looks like this, where it's like boop, 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 boop. Or if you twist like the one I just twisted, now you've got boop, 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 where it goes off on the side like that. And then you've also got one that looks like, okay, so it's 3-dimensionally. It's a little bit odd. Okay, they're all pentane because they're the same configuration. This is the one where if they're in liquid pentane, you're going to get all these different configurations. Okay? Chemically, I think they're going to behave very similarly, but if you look down at the actual level, they're going to behave. when you're taking organic chemistry class, well, they might ask you about something, what happens when you have it in this configuration or this conformation versus this conformation and reacting and so forth. So definitely a bit odd. Okay. All right, check question. These ones get a little tricky sometimes. What's the chemical formula for this? Remember how I said that, what is it? C5H12. Yeah, well, because we just saw it, right? Let's look. One carbon there, one carbon there, one carbon there, and then a carbon there and a carbon there, right? OK, so we definitely got 5 carbons. Let's see if we can count up the hydrogens. OK, carbon has 4 places where it can bond. OK, so each carbon can bond 4 places. This bond between here and here is a carbon, carbon here and a carbon here. So there's 1 coming up there. How many more places does this one have? 3. So there's going to be 1, 2, 3 hydrogens. How about off this one? 2, because you've got a carbon that way and a carbon that way. Hydrogen, hydrogen. OK, how about this one? Hydrogen, 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 hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. OK, so that's how you read these things if you're going to try to figure them out. Okay. All right. And there you go, C5H12, and we just drew that. Okay. All right. Hey, how do you get hydrocarbons? Ah, well, most hydrocarbons actually come from coal and petroleum. Okay? Well, coal and petroleum, dino juice, sometimes called dino juice. Okay? And by the way, it's not really dinosaurs. It's generally just like dead plant material. Okay? Formed 280 to 395 million years ago. So I don't know if you guys know, when you talk about peak oil, you ever heard that phrase? We're using oil, we're using oil. Well, there's only so much oil in the ground, right? And some people think that we've reached the halfway point, so that all the oil we're pulling out, we're going like downhill from the amount of oil. We've used half the oil, and it's all downhill from here in terms of using oil, right? But anyway, it's all produced millions and millions of years ago. And we dig it out of the ground, and we actually distill it. It's a little bit, it's not the same kind of distillation we talked about before. It's very similar. But what happens is you put in the crude oil, petroleum, right? And you put it into this machine that has got a little flame in there, and it heats up the petroleum, okay, and and then the vapors from that end up into this this warming container where it's warmer on the bottom and cooler on top. And what happens is the lighter hydrocarbons actually float higher and higher in this. The heavier ones stay nearer to the bottom. And so what happens is in the bottom you might get tar, and then you might get lubricants, which are a pretty heavy oil, like the stuff that you might put in your car, 10W whatever, 30 or whatever, right? Then you've got diesel, which is another relatively heavy one. Then you got kerosene, and finally you've got gasoline, and then all the way at the top here you've just got natural gas, because that never actually, even at the top of this cooling tower, it never actually becomes a liquid. But that's how you end up getting these various types of oil products out of it. Okay, that's what you have. Kerosene. What is kerosene? It's like an oil that you put in lamps generally. You got that little wick in there. Yeah, you can burn.
It's the same as the
Yeah.
fuel?
No, jet fuel is like one of the really high ones up here. Like JP5 would be another one up here, an even more refined one, I think. I'm pretty sure. Okay, all right. You guys ever hear about when your car knocks? You ever had a car? What's that?
Is it called misfire?
It can misfire. Yep, and it knocks and it creates a loud noise and whatever. What's happening is you're actually getting these nice straight molecules here, okay? And these nice straight molecules are burned very easily. And when they burn too easily in your piston in your car, when they burn too easily, they burn at the wrong time. Okay, they burn at too low a temperature, or when they're not supposed to be burning. And if they burn at the wrong time, if the piston's supposed to be going this way and to push like the gases out, but you get an explosion, it stops it and it makes it so that it's not going its full strike or full stroke, and it's bad for your car. Okay? Well, what you want is you actually want molecules that burn a little, they're actually a little harder to burn. You wouldn't necessarily think that, But you've got these other hydrocarbons, which, like in this case, this is called isoctane, which actually is a little slower burning, and they can control when it burns a little easier. And so it burns at exactly the right moment. Okay? Well, turns out that the higher octane, the more easily it is to control this, and the less burning at the wrong time you get. And so in some cases, you want your car engine to have a higher octane gas. So if you have knocking in your car, and by the way, if you hear the knocking noise, it's not necessarily knocking in your car, but if you hear that and you put higher octane gas in there, or supplements into your gas, you can actually get it to not knock anymore because you're burning at the proper time. Okay, so that's what's going on with knocking and gasoline. The way they figure out how much octane something has, they basically say heptane is an octane of 0, octane amount of 0. I don't know if it's isoctane or some other one that has, I think it is this one, an octane level of like 100, and then everything else in between, what you've got. So that's that. Okay? All right. When carbon will always form those 4 bonds. Okay? If the carbon bonds like this, okay, we call that saturated. In other words, the carbon is saturated with hydrogens. Every one of the, or I should say, or a carbon on the other side. It's just got one single bond there. You could, however, have carbon bonding like this, where the carbon and the carbon next to it, instead of having one bond between the two, it's got 2 bonds. That's going to be a slightly stronger bond. Okay? And we're going to call that unsaturated. In other words, it's not saturated with as many other atoms around it that it could have. Okay? So you look at this one. See how they're all single bonds here? That's completely saturated. If it's got these these double bonds in here, we call that unsaturated. Okay? Now this is also part of the reason you can get saturated and unsaturated fats. You've got these double bonds or single bonds, okay? And I'm not sure of all the biology about why those are necessarily bad for you, but it has to do with the fact that you've got these bonds like that, okay? All right, we've got one very special unsaturated hydrocarbon called benzene. Anybody heard of benzene before? It's actually carcinogenic. It's not so great for you. Sorry, what was that?
I've heard of that.
Yeah. Well, what is interesting about this one is it's actually a carbon ring, which is pretty cool. Here's how it works. You've got carbons, carbon, 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 and they've got double bonds inside there, like 3 double bonds. But because of the structure, it wraps around in this cool circle like this, or this cool like ring, and those bonds don't have to stay between the 2 carbons that they started with. So they can actually mix and match to where the bonds are, and so we draw it like a circle. Okay? Double bonds are not fixed. They move around the ring. Lots of organic molecules have these benzene rings. Turns out benzene's actually a fragrant sort of thing. When the benzene molecule like hits your nose, you can smell it, right? And so benzene itself, I'm not sure if benzene as itself is fragrant, but chemicals that have benzene rings in them are fragrant. And by the way, they're not always deadly, or carcinogenic, because it's part of a bigger molecule. So by itself, carcinogenic. When it's part of another molecule, probably not. But that's what causes a lot of these fragrances that you have. Okay? So benzene, anything with benzene in it is called an aromatic compound. Aromatic meaning you can smell it. Okay? All right, more benzene rings. Here's a molecule called toluene, which has a benzene ring and then one little carbon off the end there. You've got naphthalene, which is 2 benzene rings connected like this. Anybody know what they used to make naphthalene into?
They use them in the closet. Put them
In the closet. Why do you put them in the closet?
kill insects.
To kill, well, not necessarily to kill insects, but to drive away moths, mothballs. Naphthalene is mothballs. And if you've ever smelled mothballs, they've got a very pungent, some people like it, I guess, but very distinct smell. And if you put your clothes in with naphthalene over a while, your clothes kind of smell. You have to air them out when you take them out of the closet. Okay? And some other one, dichlorobenzene. You've got a benzene ring here with chlorine on one side and chlorine on the other side. Okay? Benzene rings. If you ever see that symbol, it means benzene ring. Okay. All right, check question. Ha, here we go again. What is the chemical formula for the following structure? You want to answer it all quick like last time? Let's see. What's up here? 1 carbon. What's here? 2 carbons. Is there another carbon here? No, that's just another bond. How about here? Carbon, carbon, carbon. So 1, 2, 3, 4, 5. So it's one of these two, right? OK, let's count the hydrogens. How many are up here? 1, 2, 3. How many are here?
2.
Well, let's see. You've got one carbon connected up here. You've got another carbon connected here, but it's a double bond. That's what that means. So how many bonds are off this one already? 1, 2, 3. 1 hydrogen there. OK, how about this one? 1 hydrogen. How about this one? 2, because there's only a single bond in this one. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe? Ta-da. OK, and we did the same. We drew all that out there. Not hard to do. I might ask you a couple of those on there. It's not hard, right? On the test. No, you don't want me to, or you want to? They're not hard. You can do that. Just practice it a couple times. All right. Now, we call heteroatoms atoms other than hydrogen or carbon that are actually in organic molecules. So you saw one earlier, that benzene with the chlorines on the end. That was not a hydrocarbon anymore because it had chlorine in it. Okay? Anything that's a heteroatom is a hydrogen or carbon, anything that's other than hydrogen or carbon. We have these functional groups, which are kind of cool. They're a combination of carbon, hydrogen, and some other atom that behave as a single unit. And this is how all of organic chemistry is like classified. Organic chemistry is like one giant classification thing, okay? And we're going to go through a whole bunch of these classifications in a minute. I'm not going to make you memorize them, but just see them for the first time, okay? Organic molecules are actually classified by those functional groups. It's kind of like saying there's mammals and there's insects and there's birds and whatever, right? It's the classification scheme for organic chemicals. Okay, that's what we're about to look at. Okay, so for example, here's some functional groups. Okay, you have ethane. Okay, this one is actually doesn't have any heteroatoms. It's just a hydrocarbon. Looks like this: carbon, carbon, hydrogen around the edges there. Okay, looks like that. Then you've got ethanol. You guys may be very familiar with ethanol. You get it at 11 degrees north. Maybe not for too much longer. I hear the new general doesn't like it so much. So drink your 2 beers a night while you can. Maybe I'll go down and have one later. We'll see. And then this is ethanol, but it's got this like oxygen sitting off the end of these 2 carbons. And then you've got ethylamine, which has a nitrogen instead of the oxygen there. And in fact, it's got 2 hydrogens because that's the way nitrogen actually combines. Okay, so it looks like this. That's actually blue. You can't see it there, that nitrogen. And so functional groups. Well, the functional group part, is each one of these is a functional group that acts by itself. Okay, I should say the ethyl part, ETH, is this 2 carbons with a bunch of hydrogens off there, right? Which mix together with an oxygen here, nitrogen there, nothing there. That's the functional group. Okay? All right. A little bit difficult to see here. But here's a bunch of different functional groups that we're gonna run through. Not in great detail. In organic chemistry class, you spend like a week on each one of these. And you memorize, right? At least. Alcohols look like this. Got a carbon with a little hydroxyl on there. Okay? Phenols. Oh, look, it's kind of got like a ring sort of thing. But now you've got double bonds. Right? It's a little tough to see. Right? Then you've got ethers. If you see a molecule and it has an oxygen and a carbon and a carbon like that, you say that's an ether group. Okay? You've got the amines. Okay? Carbons and nitrogens. We just saw one of those. right? Ketones. Ketones are kind of cool. Okay, we'll talk about those. They've got a little oxygen floating off this carbon, which is next to a couple other carbons. Okay, let's go over here. You've got esters, which looks like this. Again, not memorizing. Okay? Save that if you want to go to med school. Carboxylic acids look like that. Okay, they happen to be acidic. Okay. Amides, or amides, I don't know how to pronounce that one. Okay, got another nitrogen in there in a slightly different way. And you've got aldehydes, like formaldehyde, which maybe you've heard about before. Okay, aldehyde groups, looks like that. All these different groups. Again, it's like, think if I was studying, if you were studying like the classes and phylums in a biology class, right? You might go through all these things, like these are the mammals and the birds and the insects and all that. Okay, are spiders insects?
They're arachnids.
They're arachnids, I guess. Yeah, that's it. That's all the biology will do. Okay. By the way, you study organic chemistry for med school for a number of different reasons, but your body is organic, made up of lots and lots of carbon, and lots of these types of things show up when you're talking about drugs and when you're talking about the chemicals in your body and all that. I mean, this is all what it's all about. That's why they make doctors take these hard courses like this. Okay, let's look at some alcohols. Your favorite subject, right? Alcohols are organic molecules in which a hydroxyl group is bonded to a saturated carbon. Okay, remember saturated, one bond? Okay, you've got three different types of alcohol we'll talk about. Methanol. Methanol, we call it wood alcohol. It's used in windshield washing fluid. It blinds people. Unfortunately, there are a lot of cases of alcoholics, typically like homeless alcoholics, who need that alcohol fix, and they know they'll get drunk off of windshield washing fluid in your car. It's a horrible idea because it causes blindness, and it's a terrible, terrible thing. So, but these days, most windshield washing fluid is actually it might not even be windshield. I'm sorry, it's probably not windshield washing fluid. It's probably it's actually the coolant in your car. I'm sorry, I think that's what it is. It might be the windshield wash, but I think it's the coolant. But now they've changed the formulas now, so I don't think they do that. They can do that anymore. But and then you've got, of course, ethyl alcohol, okay, and you've also got isopropyl alcohol, which is rubbing alcohol, okay, like the stuff that's in the hand sanitizer. That's isopropyl alcohol. Also poisonous, so don't go drinking your hand sanitizer, right?
There were people that were trying to get drunk.
Yeah, they were also trying to die, it sounds like, too. Yeah, not such a good thing. From rubbing alcohol, yeah, you can die from that. Yeah, you don't want to do that. Now, one of the reasons when you have rubbing alcohol and you rub it against your hand, right, it cools it down a little bit too, and it evaporates relatively quickly. Well, that's part of this is because the boiling point is 97 degrees. Your hands are about 97 degrees, right? So, you know, that's why it evaporates pretty quickly. So, yeah. Anyway, look at the alcohols. So, hydroxyl group bonded to a saturated carbon. Okay, there's your saturated carbons in there, right? And you've got hydroxyls, OH, OH, OH. That's just what makes the difference in there, okay? And this is the one you'll find in beer, wine, and hard liquor. Okay? All right. Let's go on to phenols. Phenols contain what we call a phenolic group. That's what they call it, right? Phenolic group. It's this circular group, okay? Which is a hydroxyl group attached to a benzene ring. Okay? There was a guy named Lister who came up with a bunch of these things. Okay? He came up with a thing called Listerine. Right? It's got a phenol in it. Okay? And Listerine is an antiseptic, and you can use it in mouthwash. Okay? It's got a phenolic group in there. And remember, again, just because it has a benzene ring doesn't mean it's carcinogenic. You know, this little hydroxyl on the end there is probably what helps out not being carcinogenic. You've got lots of different phenols. You've got regular old phenol, which is just the benzene ring and the hydroxyl. Then you've got it's something called 4-hexyl-reso. Remember how I said at the beginning of chemistry you could make these chemical formulas like really, 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 really long? Well, you can see some of these things are really long. And if you're a chemist, you've got to know how to understand what all these things mean, right? I was never very good at it, but you've got thymol, which is like this, and it's got a couple carbons off the end. Methyl salicylate. I think this stuff is the stuff that Lister came up with. I think so. I'm not sure. Okay.
When you say benzene, my understanding of the word benzene, in Europe they say benzene to fill the car with gas. That's what the word benzene.
They fill your car with
Yeah,
benzene.
if you go to the gas station in France, for instance, and you will see the word benzene on the gas station.
Oh, really?
Yeah.
Is it the name of the station or is it the name of the
It's
stuff?
product. You tell
Oh, really?
Benzene or diesel or benzene is gas.
Interesting. It might be because of the carbons in there. They're hydrocarbons. Well, with a little yeah, benzene's a hydrocarbon, so maybe it's part of gasoline. I'm not sure. I guess it probably is. It's probably why gasoline's not so good to like huff, right? Probably not so good for you.
What are you talking about?
Yeah, exactly. All right. Then we've got ethers. Okay, ethers, carbon attached to an oxygen in the middle there. Okay, diethyl ether. So ethers are generally used for anesthetic or anesthetics in surgery. Like if you're gonna get knocked out, they might knock you out with ether. They've got that tank and they put the little mask over you and you get knocked out. Okay, it was one of the first anesthetics. Ethers. Okay. Yeah, ethers. Okay, looks like that. Okay, here's in here, the ether part is here. Oxygen, carbon, right there. Related to alcohols, they look somewhat similar to alcohols, which were here, right? You've got a hydroxyl over there. Otherwise, instead of that, you've got a little oxygen, not a hydroxyl. Kind of related. Again, if you're an organic chemist, you'll know all about the details of this. Okay. We've also got amines. Okay. I forgot. Nobody here's really been on a sub much, right? Submarine, not too much. They use amine in the oxygen on a submarine to scrub the air of like bad stuff that you don't want to breathe. I guess I don't know if it's carbon dioxide or what else other it is, but they use it in there. So and it actually smells. They're kind of offensive odors. And when you get off a sub, your clothes, you've been breathing it for so long you don't even notice it. But when you get off a sub, like your clothes smell terrible. Well, you got to wash them a few times. Like supposedly people I know whose wives, like who are on submarines, they come home and their wives are like, that bag of clothes is not even coming in the house. Like you're washing it out in here with like soap and water out here. It's so bad. There's two types of amines called putrescine and cadaverine, right? As in cadaver and putrid. These are two amines that come off of like dead bodies, right? That's like the rotting smell you get from a dead body. Are these two amines, okay? And what they have, nitrogen bonded to saturated carbon. So there's your nitrogen, okay? All right. So by the way, if you like this kind of like classification stuff, organic chemistry is for you. You get into all this stuff. Okay. All right. Then we have alkaloids. Okay. Alkaloids, they're used in medicines a lot of times. They react with acids to produce a salt, very soluble. Okay, here's one you may use every day. Right there. That's called caffeine. Okay, caffeine is an alkaloid. Okay, and what you do is you end up with caffeine. Most alkaloids exist in nature as tannins. Coffee has tannins in it. Red wine has tannins in it. Okay, naturally it has these kind of alkaloids in them. They're actually very nice and soluble in hot water, which is why when you make your tea or coffee, which have alkaloids in them, it's generally easier to make them in hot water. Yeah, Tom.
They're the antioxidant properties.
Yeah, tannins have antioxidant properties, right? Okay. So anyway, why you brew those? So caffeine. Okay. All right. We also have carbonyl groups. Carbonyl groups, carbon atom double bonded to oxygen. Carbon double bonded to oxygen. This is where you get a lot of your flavors. Yeah, carbonyl groups. Okay. Carbonyl groups occurs in a lot of these other things here that we talk about, but they're very fragrant. Things like cinnamon aldehyde, well, produces your cinnamon smell, right? You also got citral, produces your citric acid kind of smell. Okay. Benzaldehyde, vanillin. That's vanillin right there. That's what causes vanilla. Now, by the way, vanilla, you can get vanillin from the vanilla bean, right? And you can extract it out, and it's very fragrant, and it's really nice tasting and whatever. You can also make vanillin in the laboratory, which is where you get artificial vanilla flavoring. Now, artificial vanilla flavoring generally doesn't taste the same. Some people don't think it tastes as good as regular vanilla because organically produced vanilla has a lot of other chemicals in it too that kind of come along with by the extraction process. But it smells roughly the same. If you ever smelled it, it smells roughly the same. Okay? Flowers have lots of carbonyl groups in them. Okay. All right. And then amides or amides, I still don't know how to pronounce it. This you use here, hopefully regularly. It's called DEET. It's called DEET. Okay? That's the mosquito repellent. Well, turns out, according to the book, it causes mosquitoes to lose their sense of direction. When they smell DEET, they don't really know, they can't find you anymore. Right? They can't really figure out where you are. Like the way a mosquito figures out where you are is it smells you. Like that's what it is. And it's just built into a mosquito. Smells like mammals, basically, because of the carbon dioxide you put up or whatever, and hones in on you and then bites you. Well, in a place like this, where there's malaria, you don't want to get bitten very often. Not that you ever do. And as far as I'm concerned, if we completely got rid of mosquitoes, it would be perfectly fine. Some people say, well, if you got rid of mosquitoes, then things that ate mosquitoes might go away. But I've heard of studies that were done that say, you know what, mosquitoes aren't as important as we think. If you got rid of them, wouldn't really, it might be a little blip in the, in the environment, but it is a slippery slope, but I'm pretty happy to take that. I might slip a little on that one. But anyway, this is DEET, which is an amide, right? And mosquitoes makes them so they can't figure out where you are. Good news for you. You have that. Okay, and there's also esters. Okay, esters, more odors. Esters generally produce some odors like rum. Banana flavor is isopentyl acetate. Excuse me. Okay, that's a banana smell. Okay, and again, you can make artificial banana flavoring. My favorite popsicle are those banana flavored ones. Not the ones with bananas in them, like real bananas, but the banana flavored ones. It's just got this in it, basically. I love the taste. Doesn't taste much like banana, really. But again, if you have real banana extract or whatever, other stuff's coming along with it. Okay? Orange, octyl acetate. Pineapple, ethyl butyrate. Okay? And laboratories make this stuff all the time. I've read a really cool article about food laboratories for flavorings. They're all, for whatever reason, they're all in New Jersey. I don't know why. A whole bunch of them in New Jersey. And they produce these, all these chemicals, and they'll mix and match, and it's amazing how much they do. And they're tiny little drops of stuff. A lot of times you'll see natural and artificial flavors on the side of your whatever. It's because they produce this stuff in a lab. That's the artificial part. Well, natural is they extract it. And they use such a small amount of it that they never have to say exactly what it is, because it's too small to make it so the FDA cares what it is. It just makes the scent, generally. What's that? Yeah, you never know. You never know. Okay? All right, and then finally, we have these things called polymers. Polymers are long chains of monomers. Okay, monomers are just little carbon groups that are strung together like this. Okay? Polymers are important because they are generally things like plastics. Okay? Most plastic, if you didn't know it, comes from like petroleum and comes from oils and so forth. That's how they make it. They string all these things together, okay, and all these little dots in here, carbon and hydrogen, da 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 da. You have lots and lots of, like a huge long string of that. It's called polyethylene, and it's just a plastic. Okay, and in fact, they give the little recycling code for these things. If it's a 2 or a 4, it's probably polyethylene. If it's a 5, it's polypropylene, like carpet material, right? You got plastic utensils, might have a 6 on them. Okay, that's polystyrene, which you might have heard before. Okay, look, what's that? It's a benzene ring, right? So benzene ring shows up in polystyrene. Okay, and then you got polyvinyl chloride. Polyvinyl chloride is got a little chlorine in there, and it's just a whole long string. That's the stuff that makes the plastic in the side of your showers and so forth, right? I mean, the hard plastic. Like that table might be made out of PVC. This table might be made out of PVC. Okay? And you can also add other chemicals to it to soften it up. So like shower curtains and stuff, still made out of PVC. Okay? So that's that. Anyway, that was a whirlwind tour of organic chemistry. You can kind of see it's like a fascinating field. I didn't do very well in it when I took it, but it's a fascinating field. And if you ever, figure you want to, if instead of beating yourself, you want to, take a hard class, organic chemistry is a good one to take. Okay, so there's also, there's a couple more on the next page. This is continued, actually. I didn't throw them all on there, but there's more on there too. So that's actually it for chemistry. We're done with chemistry. So it wasn't too bad, was it, Frank? You wouldn't want to repeat it? Okay, well, hopefully I made it at least somewhat interesting. But anyway, on Monday, we'll do some more chemistry stuff, labs tomorrow. If you could bring your computers, that'd be good. I got to figure out exactly what we're going to do. Maybe I'll try to get that battery thing working with the electrolysis. I'll bring my lemon clock, make that. And then on Monday, we start with earth science, rocks and stuff. All right, see you then.